Now, let me stretch. Now we're going to move on to doing some examples with bijections. Specifically, we want to show how you can prove that two sets have the same cardinality. So let's just go over the definition of cardinality again. Definition, two sets, I'll say sets A and B have the same cardinality if and only if there is a bijection from A to B. Since A and B are the same cardinality if and only if there is a bijection from A to B. And cardinality basically means size. If two sets have the same cardinality, it basically means they have the same size. That's literally true for finite sets. Note, if A and B are finite, as in they have a finite number of elements, and A has the same cardinality as B, A and B have the exact same number of elements. That's just a fact, but it gets much more interesting once you're dealing with infinite cases. So the first example I'm going to do is say prove that 0, 1, so the interval 0, 1 and the interval 5 to 100 have the same cardinality. And remember, since two sets have the same cardinality, if only if there's a bijection between them, really what we're asking is, to prove this, we need to find a bijection from 0, 1 to 5, 100, or other way around. Need to find a bijection between 0, 1 and 500. And what's a bijection? Remember, a bijection is a one-to-one and onto function. It's a one-to-one and onto function, and so we have to check that's well-defined to make sure it's a function, one-to-one. So let's get to thinking. So we want to find a function from 0, 1 to 5, 100. And here's the first thing we should notice. 5, 100 is a much, much, much bigger set than 0, 1. I mean, not bigger. We're going to prove this has the same cardinality, but it spans a greater area, maybe I should say, of the number line. And so what we really need to do here is we kind of really want to multiply by something to expand. That makes no sense. Let me explain. If we had, for example, f of x were to equal 100x, that was the function we're trying to make work as a bijection. If that was the case, notice that if we look at x here, and then we look at y, like the outputs, right? We have, we have x here, which is 0, goes from 0 to 1. Let's say this is 100. This is 0. this is 50, this is 75, this is 25. If you notice, if I talk about 100, 0 times 100 is 100. 0 times a quarter is 25, or sorry, a quarter times 100 is 25. A half times 100 is 50. 3/4 times 100 is 75. And then 1 times 100 is 100. So if you notice here, what's happening is, if you do f of x equals 100x, and then you plug in everything in 0, 1, it's gonna just spread everything out between 0 and 100. Because 0 times 100 is 0, 1 times 100 is 100, and we hit everything else in between. Hope that makes sense. So multiplying by 100 just kind of spreads everything out, really. But we really don't want, this interval doesn't cover 0. This interval doesn't cover like an area of 100 length. It covers an area of like 95 length, right? 5 to 100. So we really want here is not f of x equal 100x, but f of x equals 95x. So then this will cover, once you plug in everything between 0 and 1, the range of this will range between 95 times 0, which is 0, and 95 times 1, which is 95. So this will range between 0 and 95. But that's not quite the same interval we have here. Right? This interval is 5 to 100, not 0 to 95. We want to shift our interval. If we add 5 to this, when you plug in 0, f of 0 is going to give you 95 times 0 plus 5, which is 5. When you plug in 1, you get 95 times 1 plus 5, which is 95 plus 5, which is 100. The plugging things in between will get us everything in between. So this is a very good candidate for our function. So let's let f of x equal 95x plus x. And now let's try to prove it's actually a bijection. So to be a bijection, we need to prove the following things. We need to prove be a bijection. We need to prove that f is well-defined 1-to-1. I don't want to. So let's do well-defined first. So is our function f here well-defined? Yeah. Function f is totally well-defined. Why is it totally well-defined? Well, because it's made up of 95 times x plus 5. And for each input, 95 times x is one output. And add 5 to that, it's still just one output. So note, for each input in the domain, oh, by the way, we should specify here that f goes from 0, that f goes from 0, 1 to 5, 100, just like we want, by f of x is 95, x plus 5. Good. So for each input in the domain, which is 0, 1, 95x has one output, and thus the sum of 95x and 5 has one output. So f has exactly one output. So for each input, f has exactly one output. Therefore, f is well-defined. Now let's move on to 1-to-1. So I'm going to say that f is 1-to-1. And the reason being is because 95x plus 5, it doesn't seem like it would loop back around in itself. I think any two distinct inputs here will go to distinct outputs, especially because 95x plus 5, again, is increasing. So if you plug in two numbers, different numbers, well, one's going to be bigger than the other. So I expect 95x, I expect f of 1 to be bigger than f of the other, basically. So let's prove 1 to 1. We're going to prove that. Goes like this. We always do the same thing. We assume there's two elements in the domain, just that f of a plus f of b, and then prove a must equal b. Assume there exists a, assume there exists a and b in the domain, which is 0, 1. Oh, such that f of a equals f of b. We want to show a equals b. Note, by definition of f equals 95x, f of x equals 95x plus 5. Since we have f of a equals f of b, we get 95a plus 5 equals 95b plus 5. Subtracting 5 from both sides, 95a equals 95b. Dividing 95 for both sides, a equals b as desired. Thus, f is 1 to 1. So you've shown that if there are two inputs, that when you plug in, you get the same output. Those two inputs must be the same. There can't be two distinct different inputs that you plug in and get the same output. Therefore, f is 1 to 1. So we're like 2/3 of the way there to being a bijection. The last thing we need to show is that f is onto. All right. And this is actually going to be maybe the easiest one of them all, because we did just some really simple algebra here. Because all I have to show is that if there's a y in 500, we can find an x that we can plug in here to get to that. So we want x such that 95x plus 5 equals 100. Or sorry, no, equals y. We'll plug it in so it equals y. When x is 95x plus 5 equals y. But that implies that 95x equals y minus 5, which implies that x is going to equal y minus 5 over 95. It seems you plug in y minus 5 over 95 into f, you'll recreate y. So the only thing we have to show is that x is actually in a domain, which is going to be not that much. I'm going to erase the 1-to-1 part, though. Give me some more room. So proof, want to show for all y in the codomain, which is 5 to 100, there exists an x in the domain 0, 1, such that f of x equals y. To that end, let y be any arbitrary / particular element of 5, 100. And then like you can't see what I'm doing. Hold on here. Here we go. And then, like we showed in our little green aside, let x equal y minus 5 over 100. Is that what I want? No. Y minus 5 over 95. That's what we said in the thing before. There we go. Y minus 5 over 95. Note, since y is in 5 or 100, 5 is less equal to y, and y is equal to 100. Thus, we subtract 5 from both sides here. 0, which equals 5 minus 5, is this one equal to y minus 5? And y minus 5 is equal to 100 minus 5, which equals 95. Thus, 0 less than equal to y minus 5 less than equal to 95. Then, since 0 less than equal to y minus 5, we have that 0 over 95 just equals 0 is going to be less than or equal to y minus 5 over 95 by dividing both sides by 95. And since y is less than or equal to 95, y over 95 is going to be less than or equal to 95 over 95, which equals 1 by dividing both sides by 95 again. And since 95 is positive, you divide by a positive number, you don't have to change the signs or anything like that. Thus, 0 less than or equal to y minus 5 over 95 less than or equal to 1. So, y minus 5, so x, which equals y minus 5 over 95, truly is in 0, 1. So x really is an element of the domain. So x really is an element of the domain. Now it just shows that this particular x you can plug into f to get y. If you can show that, that means that there does in fact exist an x you can plug into f to get y. What it shows it's onto 1 to 1, 1 to 5, meaning is a bijective function. So we have a cardinality. This is a lie. Okay, let's go. Next, note that f of x will equal 95x plus 5 by definition, which will then equal 95 times y minus 5 over 95, because that's what x we said equals, plus 5 by substitution. And then the 95 is going to cancel out here, so we get y minus 5 plus 5 by simplification just equals y by more simplification. Thus, x is, so thus, for any y in 5 to 100, the codomain, there does exist an x in the domain such that y equals f of x. Hence, f is onto. Okay, that's our proof right there. So this shows that f is onto, because for any y you give me, any y you pick in the codomain, I can find x in the domain, mainly just by taking that y, subtracting 5 and dividing it by 95, that I know I can plug into f and get that y back out. So every single y is hit by a particular x. All right, so putting this all together, so all together, or do I want all together? Now I forgot what basic English means. Let's just go all together like this, all together. I feel like there's a pause in there. All together. F is well-defined, 1-to-1, and onto. So f is a bijective function from the domain 0, 1 to codomain 5, 100. Hence, 0, 1 and 5, 100 have the same cardinality as, or are the same cardinality. Meaning in a certain sense, they have the same size. So in a certain sense, our sets here, 0, 1, and 5, 100 have the exact same cardinality, even the exact same size, because of the conformance bijection. Okay,